Welcome to Orbit into Sleep. Tonight we are drifting somewhere wonderful. The title of this video is Relaxing Sputnik Facts to Fall Asleep To. No mid-roll ads, just you, a soft voice, and the quiet hum of history floating somewhere above the earth. So before we begin, if you are already tucked in, maybe your phone resting on the pillow beside you, or propped gently on your nightstand. Hello, I am so glad you are here. This channel exists for exactly this moment, that in-between place where your day is done, your body is still, and your mind just needs somewhere calm to go. And tonight, we are going to give it something genuinely fascinating to rest inside. We are talking about Sputnik, a little silver ball, smaller than you might imagine, that changed everything. And there are so many extraordinary, quietly wonderful things to know about it. Things that almost nobody talks about. Things that are perfect for a sleepy mind to turn over slowly, like a smooth stone in your palm. Now, before we drift off together, I do have one small, gentle favor to ask. If you are enjoying what we do here at Orbit into Sleep, and these kinds of videos have been helping you drift off at night, would you consider giving us a like? And if you are not already subscribed, a subscription truly does help other people, perhaps someone lying awake right now, just like you, find their way here too. It means so much more than you know. And one more little thing I would absolutely love to know. How many hours of sleep do you normally get per night? Pop it in the comments when you wake up. Are you a solid 8-hour sleeper, a restless 5, somewhere in between? I am genuinely curious, and it helps us understand who we are making this for. All right, get comfortable, adjust your pillow, let your shoulders drop, and let's begin. A little silver ball called the simplest satellite. Let's start right at the beginning, and I mean the very beginning, because before Sputnik became the most famous object ever launched into space, it almost never existed at all. The original plan, you see, was far more ambitious. Soviet scientists had designed something called Object D, a grand, sophisticated scientific laboratory weighing around 1,400 kilograms, packed with instruments, bristling with technology, meant to be a genuine orbital research station. It was going to be extraordinary, but extraordinary has a habit of taking longer than expected. The rocket that would carry it into space, the magnificent R-7, was still being refined. It wasn't quite ready to lift something that heavy with complete reliability. And meanwhile, there were whispers, rumors that the Americans were close to launching their own satellite, something called Vanguard, as part of an international scientific program called the International Geophysical Year. And so Sergei Korolev, the brilliant, quietly driven man at the heart of the Soviet space program, a man known simply as the chief designer, because even his name was a state secret, made a decision. He proposed something almost audaciously simple. Forget Object D for now. Forget the grand laboratory. Let's launch something small, something light, something that would work, something that would get there first. And that something became PS1, Prostishai Sputnik, which translates rather beautifully as the simplest satellite, Now here is where I want you to hold a picture in your mind, because it's a lovely one. Imagine a beach ball, a polished, gleaming, silvery beach ball. That is roughly the size we are talking about. 58 centimeters across, just under 2 feet in diameter, weighing 83.5 kilograms, so not something you would want dropped on your foot, but still, for something that changed the entire course of human history, it was remarkably modest in size. The sphere was made from 2 halves, 2 beautifully crafted hemispherical shells, joined together with 36 bolts and sealed with rubber O-rings. And the material those shells were made from was something called the AMG6T alloy, an aluminium, magnesium, and titanium blend. The titanium, in tiny amounts, acted as what engineers call a grain refiner, which is a lovely phrase, isn't it? A grain refiner. It sounds almost meditative. What it means is that during the forging of those 2-millimeter thick shells, the titanium prevented the metal from developing coarse internal structures, tiny potential fracture points that might crack under pressure, because there would be pressure, literally. The inside of Sputnik was filled with dry nitrogen gas at 1.3 atmospheres, just slightly above the pressure of the air in this room. This wasn't just to protect the electronics. It was actually the satellite's primary scientific instrument for detecting micrometeoroids. The idea being that if even a tiny particle punched through the shell, the pressure would drop and the radio signal would change. We will come back to what happened with that in a little while, because the result was quietly extraordinary. But for now, just rest with that image. A small, perfect sphere, polished to a mirror finish, sealed tight, filled with nitrogen, with 4 slender antennas trailing behind it like the legs of a spider. 2 of them 2.4 meters long, 2 of them 2.9 meters long, all angled backwards at 70 degrees, giving the whole thing a kind of elegant arrow-like silhouette. This was the object that on the 4th of October 1957, at 19 hours, 28 minutes, and 34 seconds, Coordinated Universal Time, rose from the steppes of Kazakhstan and became the first human-made object to orbit the Earth. It traveled at approximately 8 kilometers per second. Let's sit with that for a moment. 8 kilometers every second. That means in the time it takes you to draw a single slow breath right now, Sputnik would have covered something like 40 kilometers. While you are breathing in, it has already crossed a small country, and it completed a full orbit of the Earth every 96.2 minutes, over and over and over again, while people slept, while children went to school, while the world carried on, largely unaware. This little silver ball was looping silently around the planet, beeping, that beep. The beep is such a part of the story that it almost overshadows everything else. But it is worth understanding gently what that beep actually was, because it wasn't random. It wasn't just a noise, it was carrying information. The radio transmitter, called the D200 system, broadcast on 2 frequencies simultaneously. 20.005 megahertz and 40.002 megahertz. These two frequencies were chosen very deliberately. They allowed scientists to study how radio waves of different wavelengths passed through or bounced off the layers of ionized gas high in the atmosphere, the ionosphere, a region of the sky that radio operators had known about for decades but had only ever studied from below. Sputnik was the first chance to study it from above. The pulse of the beep, its duration, that 30 to 40 millisecond rhythm, was controlled by a clever little circuit involving a capacitor and something called magnetically latching relays. And here is the part I find quietly wonderful. These relays were designed to hold their position using a permanent magnet, so they only needed electrical current in the moment of switching, not in between. This saved precious power from the 3 silver-zinc batteries nestled inside the sphere. It was an act of engineering elegance, doing more with less, whispering rather than shouting. Now, those batteries were designed to last 2 weeks, and they lasted 22 days. Until the 26th of October, 1957, at which point the signal fell silent. But Sputnik itself kept going. It continued orbiting the Earth, silent now, for another 2.5 months. Until the 4th of January, 1958, when it re-entered the atmosphere and burned up after completing 1,440 orbits. 1,440 quiet laps around this planet. And here is one more thing to carry with you as you settle deeper into your pillow tonight. If you had been standing outside in those early autumn evenings of October 1957, looking up at the night sky, hoping to spot Sputnik, you almost certainly would have been looking at the wrong thing. The satellite itself, that polished sphere, was actually very difficult to see. Its brightness magnitude was somewhere between +6 and +8, right at the very edge of what the naked human eye can detect on a perfect night. Most people, in most places, simply could not see it. What they saw, and what millions of people reported watching glide silently across the sky, was the rocket. The enormous 28-meter core stage of the R-7 that had carried Sputnik into orbit. That was bright, first magnitude bright as the brightest stars in the night sky. A slow, steady, silent traveler. It orbited along a very similar path to the satellite, and it stayed up until January 4th, 1958. The same day Sputnik burned up, so in a way, those millions of people watching the sky weren't watching the satellite at all. They were watching the ghost of the launch, the beautiful, unintended, accidental spectacle of the rocket that let go. There is something rather poetic about that, I think. The thing that changed the world, small, silver, almost invisible, and the thing people watched without knowing exactly what they were seeing, the spent shell of the effort it took to get there. Let that thought drift with you now. A little silver ball moving silently through the dark above the earth, watched by millions without being seen, beeping its quiet data into the ionosphere asking questions that nobody had thought to ask before. We will explore some of the answers in a little while, but for now, just breathe. Let your body settle. You are exactly where you need to be. The rocket that carried the dream. Now that we know what Sputnik was, let's think about how it got there. Because the satellite itself, as wonderful as it is, was only possible because of something rather extraordinary sitting beneath it, something enormous and thunderous and bristling with engineering ingenuity. The R7 Semyorka. Semyorka is a Russian word that means simply the number 7, and it is a rather understated name for what was, at the time, the most powerful rocket ever built. The world's first true intercontinental ballistic missile, and the machine that, with a few modifications, became the launch vehicle that carried Sputnik into history. Let's picture it together because the image is genuinely striking. Imagine standing at the base of a rocket that is over 30 meters tall. That is roughly the height of a 10-story building. And it is not a single cylinder, like you might picture from old science fiction films. It is a cluster, a central core, surrounded by 4 strap-on boosters attached to its sides, each one tapering to a point at the bottom. Engineers called this a packet configuration. And the remarkable thing about this design is that all 5 sections, the core and all 4 boosters, ignited together on the ground, not in stages like later rockets would do, all at once, right from the moment of launch. This was partly a technical necessity. The engines of the time needed to be firing at full power before the rocket left the pad to generate enough thrust to lift such an immense weight. But it also meant that the sound and the fire and the sheer physical force of that ignition would have been overwhelming. A wall of thrust from 32 main combustion chambers all roaring together. Let's talk about those engines for a moment because they are quietly fascinating. The 4 strap-on boosters each carried an engine called the RD-107. The central core carried a slightly different version called the RD-108. These 2 engine types shared much of their basic architecture, the same fundamental turbopump design, the same general principles, but they differed in one important way: their steering systems. You see, on a rocket, pointing yourself in the right direction is just as important as going fast. And the R7 didn't steer by tilting its main engines, as many modern rockets do. Instead, it used something called vernier engines, smaller secondary chambers mounted around the outside of each main engine, which could be angled slightly to nudge the rocket in the desired direction. The core stage had 4 of these verniers. Each booster had 12 small steering chambers in total, working in careful coordination to keep this enormous machine on its precise mathematical course. Now, the fuel that powered all of this was a combination of liquid oxygen and kerosene. And here is a detail that I love for its unexpectedness. The inner walls of the combustion chambers, where temperatures reached several thousand degrees, were made from a chromium-bronze alloy. And running through those walls were channels just 5 millimeters deep, through which kerosene flowed before it entered the combustion chamber. The fuel itself was doing the cooling. circulating through the walls of the very chamber it was about to burn inside. Engineers call this regenerative cooling, and it is one of those ideas that feels, once you understand it, almost impossibly elegant. The engines were started not with a spark or a flame, but with a carefully controlled chemical reaction. Hydrogen peroxide, that familiar household antiseptic, was used in a highly concentrated form to drive the turbopumps. When this concentrated hydrogen peroxide was passed over a catalyst, it decomposed very rapidly into high-temperature steam and oxygen. That steam spun the turbines that pushed the propellants into the engines. It is a lovely example of one chemical reaction being used to enable another, much larger one. And while we are on the subject of unexpected engineering moments, there is one story from the preparations for the Sputnik launch that I think deserves to be told quietly at night, because it speaks to something very human about all of this. Just before the launch that would carry Sputnik into orbit, there had been a test flight attempt designated M1-6. The rocket was prepared, fueled, placed on the pad, and then someone noticed something. A nitrogen scavenging valve, a component responsible for clearing propellant lines safely, had been installed backwards. The entire rocket had to be taken off the pad and corrected. A single valve, facing the wrong way, on a machine with thousands of components, and someone caught it. I find that quietly wonderful. Not the error, but the catching of it, the attentiveness, the care. The fact that somewhere in that enormous program, under immense political pressure, with the eyes of a nation and the weight of the Cold War pressing down, someone still stopped and said, "Wait. Something is not right. Let me look again." Now, once the rocket was flying, it needed to know where it was going, and this is where the guidance system comes in. The R7 used something called the V142 gyro horizon, a uniaxial stabilized platform that maintained the rocket's programmed course with extraordinary precision. Alongside this was the V139 accelerometer, which measured the rocket's speed using the precession force of an unbalanced gyroscope. As the gyro spun and was acted upon by the rocket's acceleration, it tilted. And the degree of that tilt told the guidance system exactly how fast the rocket was going. The target speed at engine burnout was approximately 8,000 meters per second, just over 8 kilometers every second, and the sequence of events at that moment was carefully choreographed. The engine shut down. There was a 20-second pause. Then a spring-loaded mechanism released the conical nose fairing, the protective shell around the satellite. Then a pneumatic piston gently pushed Sputnik away from the core stage. And finally, a small residual jet of oxygen was fired to push the spent rocket body in a slightly different direction so that it wouldn't drift back and collide with the satellite it had just released. That last detail, the little puff of oxygen to nudge the rocket away, is now standard practice in spaceflight. Every time a satellite is deployed safely into orbit today, that principle, that small act of careful separation, traces a direct line back to this moment, to October 1957, above the steppes of Kazakhstan. The rocket, having done everything it was built to do, fell into its own orbit. That same 28-meter cylinder that millions of people watched crossing the night sky. The beautiful, accidental spectacle we talked about in our last chapter, while Sputnik beeped on quietly above. And where did all of this happen? Let's take a slow moment to think about the place itself, because Baikonur is a name that has become almost mythological in the history of space exploration, and its beginnings were remarkably modest. The site was officially designated NYYP-5. It was located near a small railway town called Tyuratam, in what was then the Kazakh Soviet Socialist Republic. A flat, semi-arid landscape of enormous skies and very few people, which was rather the point. The Soviet ICBM program required secrecy, and it required distance, enough of it that the rockets could follow their planned trajectories without inconvenient observers. Construction of the launch facilities began in July 1955, just 2 years before the Sputnik launch. Military construction units worked through the punishing heat of Central Asian summers and the equally punishing cold of its winters. The first R-7 rocket arrived at the site in March 1957, and just 7 months later, in October, the first satellite left from there to circle the Earth. 2 years from empty step to the beginning of the space age. There is something almost dreamlike about that timeline, the speed of it, the scale of human effort concentrated into that flat, windswept place. Today, Baikonur is a city. It has streets and schools and a museum. It hosted human spaceflight for decades. Cosmonauts and astronauts have departed from that same general area for the International Space Station within living memory. But in October 1957, it was a remote collection of concrete and ambition, surrounded by the vast quiet of the Kazakh steppe. And on one clear autumn night, it briefly became the most significant place on Earth. The R-7, for all its power, was in one sense just a means to an end, a delivery mechanism, a way of imparting enough velocity to a small silver sphere that the sphere could fall around the Earth forever, or very nearly forever. The rocket's job was to hand the satellite to physics and then get out of the way, and it did exactly that. Let that settle for a moment. The tremendous, thunderous, carefully engineered effort of the launch. And then the silence afterwards. The satellite, alone in its orbit, the rocket falling behind, the Earth curving away below. A quiet beep in the darkness, going around and around and around. You are doing beautifully. Keep breathing slowly. Let your thoughts drift where they want to. We have more to explore together, but there is no hurry at all. The night is long, and we are in absolutely no rush. What the beep was telling us, so Sputnik is up there, orbiting, beeping, and the world is listening. But what exactly was it saying? This is the part of the story that I think deserves far more attention than it usually gets, because the popular image of Sputnik is of a simple thing, a ball that went beep, a political gesture dressed up as science, something whose significance was symbolic rather than substantive. And that picture is not quite right. The signals coming from that small silver sphere were doing something genuinely remarkable. They were, for the first time in human history, allowing scientists to study the upper atmosphere from the inside, or rather, from above, from within the very region they had spent decades trying to understand from a distance. Let's talk about the ionosphere, because it is a beautiful and strange place, and it deserves a gentle introduction. High above the Earth, roughly between 80 and 1,000 kilometers up, the sun's radiation, particularly its ultraviolet light and X-rays, strips electrons away from gas molecules. What you are left with is a region of partially ionized plasma, gas that carries an electrical charge. This is the ionosphere, and it has a profound effect on radio waves. Some frequencies bounce off it, which is how AM radio signals travel far beyond the horizon. Others pass straight through it, and the exact behavior depends on the frequency of the wave and on the density of the ionized plasma at any given moment. Before Sputnik, scientists had been studying the ionosphere entirely from the ground, bouncing radio signals up and measuring what came back. It was a bit like trying to understand the ceiling of a room by throwing a ball at it and watching where it lands. You could learn something, but there was so much you couldn't see. Sputnik changed that. The two transmission frequencies, 20.005 MHz and 40.002 MHz, were chosen with great care by a physicist named Konstantin Gringaus. The lower frequency, around 20 MHz, was selected because it sits close to what is called the critical frequency of the ionosphere's F layer. The F layer is the most highly ionized region, sitting at altitudes of roughly 200 to 500 kilometers. At its critical frequency, radio waves are right on the boundary between being reflected back to Earth and passing straight through, which means signals at this frequency are exquisitely sensitive to changes in electron density. The higher frequency, 40 MHz, behaved differently. It passed more readily through the ionosphere, allowing scientists to study how the signal changed as it did so. By comparing how both signals behaved simultaneously, scientists could derive information about electron density at various altitudes. And because Sputnik was orbiting above the ionosphere, rising and setting from the perspective of any given ground station multiple times a day, they could track how those conditions changed over time, over geography, and over the course of the day and night cycle. This is where the work of Professor Jakob Alpert and his team at an institute called ISMIRAN becomes quietly extraordinary. Alpert noticed something in the fine structure of the signals. The way the beeps arrived was not perfectly regular. There were subtle variations, tiny fluctuations in the signal that, when analyzed carefully, revealed that the ionosphere was not the smooth, layered, well-behaved medium that existing textbooks described. It was turbulent, patchy, dynamic, full of discrete clouds of ionized gas moving at high velocities. The ionosphere, it turned out, had weather, not in the way we experience weather on the ground with rain and wind and pressure systems, but its own kind of internal variation, its own structure and motion and change. Alpert's analysis of the Doppler shifts in Sputnik's signal, the slight changes in frequency caused by the satellite's motion relative to the observer, allowed him to estimate the densities and velocities of these ionospheric clouds. It was the first experimental proof of ionospheric turbulence at altitudes above what is called the F2 maximum, the very top of the most active ionospheric layer. These findings had immediate practical consequences. Understanding how the ionosphere behaves is essential for radio communications, for navigation systems, for anything that relies on signals passing through or bouncing off that region of the sky. Alpert's work, born from listening carefully to Sputnik's beep, improved the accuracy of all of these things. But there was something else the signal was doing, something more intimate in a way. Remember the nitrogen inside the sphere, the pressurized atmosphere at 1.3 atmospheres, and the barometric switch set to trigger if the pressure fell below 0.35 kilograms per square centimeter, roughly a third of normal atmospheric pressure. If a micrometeoroid, even a tiny one, had punctured the shell, the pressure would have dropped and the circuit would have responded. The magnetically latching relays inside the transmitter would have switched states, and the rhythm of the beep would have changed. The pulse duration would have shifted from its normal 30 to 40 millisecond pattern to a noticeably different ratio, one pulse length against a different one. A binary signal embedded in the timing of the beeps that would have told the scientists on the ground, something has hit us. For 22 days, that change never came. The pressure inside Sputnik held steady throughout the entire mission, and this absence of a signal, this non-event, was itself a discovery. Scientists had predicted, based on theoretical models, that the density of micrometeoroids in low Earth orbit would be fairly significant, enough to pose a meaningful risk to spacecraft. But Sputnik's quiet, uninterrupted beep suggested that the actual density was lower than the models had assumed. This finding influenced spacecraft design for years. The shielding assumptions built into early satellites and capsules were adjusted in light of what Sputnik's nitrogen did not report. The dog that did not bark, as the saying goes. The hole that was not punched. The beep that did not change. Science done through listening for something that never happened. And then there is the thermal side of the story, because the electronics inside Sputnik were sensitive. Vacuum tubes and relays and capacitors do not enjoy extremes of temperature. And in orbit, a satellite experiences both. On the sunlit side of the Earth, solar radiation can heat a surface intensely. On the night side, with no atmosphere to retain warmth, temperatures plunge. The way Sputnik managed this was through a system called the DTK-34, and it had two elements. The first was the polished mirror finish of the outer shell, which we have mentioned before. That mirror surface was not just for aesthetics or visibility. The reflectivity of the surface was carefully calculated to balance the amount of solar energy absorbed against the amount radiated away as heat. The sphere was its own passive thermal regulator to a degree, but passive regulation was not enough on its own. Inside, a small fan was connected to a temperature sensor. If the internal nitrogen temperature rose above 30 degrees Celsius, the fan switched on, circulating gas within the sphere and moving heat from the warmer electronics toward the cooler aft hemisphere. Once the temperature dropped back to 23 degrees, the fan switched off again. A small fan inside a metal sphere in orbit, doing its quiet work. There is something rather soothing about that image, I find. The hum of a fan, the gentle circulation of nitrogen in the dark, the sphere maintaining its own small internal climate, thousands of kilometers above anyone who might notice. And the DTK-34 worked. Throughout the 22 days of active transmission, the electronics functioned within their designed temperature range. The thermal control system, for all its simplicity, performed exactly as intended. Now, all of this, the ionospheric mapping, the micrometeoroid monitoring, the thermal management, was being observed and recorded by a network of stations across the Soviet Union. 13 scientific measurement stations, designated NYPs, spread across the enormous geography of the USSR. These formed what was called the KIK network, the Command and Measurement Complex, centered at a facility near Moscow. But the Soviet network was not the only one listening. In England, in the Cheshire countryside, there was a radio telescope, enormous even by today's standards. A steerable dish 76 meters across, mounted on a structure that could turn to follow objects across the sky. The Mark I telescope at Jodrell Bank Observatory, built under the direction of a physicist named Bernard Lovell, and completed just weeks before Sputnik's launch. Almost as though the universe had arranged the timing deliberately. Jodrell Bank had been built to study cosmic radio sources, distant galaxies, the remnants of supernovae, things so far away that their signals arrived as the faintest of whispers. But now, here was something broadcasting quite loudly from only a few hundred kilometers up, circling overhead several times a day. The Mark I telescope tracked the carrier rocket of the Sputnik launch by radar. On the 12th of October, 1957, just 8 days after launch. And in doing so, it provided the first definitive, independent Western confirmation that the Soviet achievement was real. Before that moment, there had been those in the United States who suggested, or perhaps hoped, that the whole thing might be a hoax, a propaganda exercise, a signal broadcast from the ground pretending to be from orbit. Jodrell Bank's radar return from the rocket body settled the question. There was something up there, something large and moving at orbital velocity on a precise Keplerian trajectory around the Earth. It was real. Bernard Lovell's telescope became, almost overnight, one of the most important scientific instruments on the planet. And the relationship that developed between Jodrell Bank and the Soviet space program was quietly remarkable. In the years that followed, the Soviets would actually request Jodrell Bank's assistance in tracking some of their lunar missions. An English radio telescope in a Cheshire field helping the USSR navigate to the moon. A small human moment of scientific cooperation inside the larger coldness of the Cold War. Let that sit with you for a moment. The idea that science, even in the most politically fractured of times, has a tendency to reach across the lines that politics draws. The beep of Sputnik traveled through the ionosphere. It was helping to map, bounced around the Earth, was heard by amateur radio operators in their garden sheds, by professional scientists in purpose-built stations, by farmers who had built their own receivers from magazine instructions. It was heard in Australia and Argentina and Japan and Canada. It was heard by people who had no idea what they were hearing and by people who understood exactly what it meant. A signal from above, small and regular and calm, asking the universe very gently to show itself. And the universe, rather wonderfully, did. Rest here for a moment. You are doing so well. Let the images settle. The spinning sphere, the listening dishes, the electron clouds drifting in the high dark. There is no rush at all. Just breathe and let it all float there quietly above you. We will carry on in just a little while, when the world looked up and changed. So far, we have spent our time close to the satellite itself, inside its polished shell, inside the roar of its rocket, inside the frequencies of its signal. But now I want to gently pull back, to take the longer view, because what happened after Sputnik beeped for the first time was not just a scientific story, it was a human one. And the human story is, in its own way, just as extraordinary. Let's begin in the United States, because the reaction there was unlike almost anything that had happened in peacetime. The word that gets used, and it is the right word, is crisis. The Sputnik crisis, a moment when an entire nation looked up at the night sky and felt, quite suddenly, vulnerable. But here is the thing. The fear was not really about the satellite, not about the beeping ball itself. Nobody was lying awake worrying that an 83-kilogram sphere was going to hurt them. The fear was about what the satellite implied. To put a satellite into orbit, you need a rocket powerful enough to accelerate something to 8 kilometers per second. You need to lift it above the atmosphere. You need guidance systems precise enough to achieve the exact insertion angle and velocity. You need engineers who understand orbital mechanics at a deep and practical level. And if you have all of those things, you also, almost incidentally, have the ability to send a nuclear warhead to the other side of the world. The R-7 that carried Sputnik was not built as a satellite launcher. It was built as an intercontinental ballistic missile, the world's first, designed to carry a thermonuclear warhead from Soviet territory to American cities. The satellite was, in a sense, its proof of concept, a demonstration conducted in full view of the entire world that the technology worked. Before October 4th, 1957, the American defense strategy rested partly on geography. Two vast oceans, thousands of kilometers of water between the continental United States and any potential adversary. Traditional weapons required ships or aircraft to cross that distance, and ships and aircraft could be intercepted. But a ballistic missile, arcing through the upper atmosphere at 8 kilometers per second, could not. The ocean suddenly meant nothing. President Dwight Eisenhower tried initially to project calm. He had been briefed in advance by his intelligence services. He knew that the Soviet space program was close to this achievement, and in private, he was not entirely alarmed. He had his own classified reconnaissance programs, and he had a reasonably clear picture of Soviet military capabilities. But publicly, the reaction was very different. The press coverage was extraordinary. Politicians competed to express the most urgent concern. And then, just 2 months later, the situation became rather worse. The United States Navy had its own satellite program. It was called Vanguard, and on the 6th of December, 1957, in front of live television cameras, it attempted to launch its first satellite. The rocket rose about 1.2 meters off the launch pad, and then it sank back down, and then it exploded. The satellite, small and spherical, was thrown clear of the fireball and landed in the grass beside the pad, where it sat transmitting its little signal, having technically never left the ground. The newspapers were not kind. The rocket was called Flopnik, Stayputnik, Kaputnik. It was a moment of profound national embarrassment at precisely the worst possible time. And from that embarrassment came change, significant, lasting, institutional change. In July of 1958, President Eisenhower signed the National Aeronautics and Space Act. This transformed an existing government body, the National Advisory Committee for Aeronautics, which had existed since 1915 and done genuinely excellent work in aviation research, into something new, something with a broader mandate, something that looked outward as well as upward. The National Aeronautics and Space Administration, NASA. It is worth pausing on that transition. The NACA, as it was known, was a research institution. Quiet, technical, unglamorous. It produced reports and wind tunnel data and aerodynamic theory. It was precisely the kind of organization that rarely makes the news. NASA was built on those same foundations, with the same engineers, the same institutional knowledge, the same culture of careful technical work. But it was given a different purpose, a more visible one. And over the years that followed, it would put humans on the moon, send probes to every planet in the solar system, and place a telescope in orbit that showed us the edge of the observable universe. All of that traces back in a direct institutional line to the moment a small Soviet satellite beeped overhead and made Americans feel that they needed to respond. At the same time as NASA was being created, another organization was born. The Advanced Research Projects Agency, which we know today as DARPA, created specifically within the Department of Defense to prevent future technological surprises, to look further ahead, to fund the strange, the speculative, the long-term, the kind of research that does not have an obvious, immediate application, but might, in 10 or 20 years, change everything. DARPA went on to fund, among other things, the early research into networked computing that eventually became the Internet. So, in a rather roundabout way, Sputnik's beep is part of the long causal chain that connects to the device you are listening to this on right now. History has a way of doing that. And then there was education. because one of the questions that Sputnik raised loudly and urgently was this: how do we produce more scientists, more engineers, more mathematicians? How do we ensure that the next generation has the skills to compete in this new world? The answer came in the form of the National Defense Education Act of 1958, a piece of legislation that represented a massive federal investment in education, specifically focused on science, mathematics, engineering, and languages. It funded university scholarships. It funded the purchase of laboratory equipment for schools. It funded teacher training. It reshaped the American education system at a foundational level. Children who were in primary school in 1958 grew up in classrooms that had been changed by Sputnik's shadow, curricula that had been revised, resources that had been allocated, an emphasis on scientific literacy that had not existed before. Some of those children went on to work at NASA. Some of them built the computers that made the Apollo program possible. Some of them became the scientists and engineers who designed the satellites that now make GPS work, that carry our phone calls, that monitor our weather and our climate, the ripples from a single beep spreading outward through time. Now, beyond the United States, there was another consequence of Sputnik that tends to get overlooked, a legal one, and it is quietly fascinating. Before October 1957, the legal status of outer space was completely undefined. Nations claimed sovereignty over the airspace above their territory, which meant in theory that every time Sputnik passed over a country, it was violating that country's sovereign airspace. The Soviet Union could, technically, have been in breach of international law with every single orbit. Nobody actually pursued this. Nobody filed a legal complaint, but the question hung in the air, so to speak. And what the Sputnik launch did, by happening during the International Geophysical Year, a cooperative scientific program involving 67 nations, was establish a precedent, a quiet de facto agreement that orbital space is different from airspace, that the right of overflight in orbit is not a violation of sovereignty, that space beyond a certain altitude belongs to no one nation and is open to all. This principle was eventually formalized in the Outer Space Treaty of 1967, which remains the foundational document of international space law. It prohibits nations from claiming sovereignty over the moon or other celestial bodies. It prohibits the placing of nuclear weapons in orbit. It establishes that space exploration should be carried out for the benefit of all countries. Every satellite that orbits the Earth today, from GPS navigation systems to weather satellites to the International Space Station, does so under a legal framework whose cornerstone was laid by Sputnik, passing silently over the countries of the world and nobody in the end objecting. There is one more thread I want to follow before we rest here for a while, because there is a discovery made in the immediate aftermath of Sputnik's launch that is almost unbearably elegant in its unexpectedness. At the Applied Physics Laboratory of Johns Hopkins University, two researchers named William Guire and George Weifenbach were listening to Sputnik's signal, not because they had been asked to, not as part of any official program, just because they were curious and because the signal was there and because they were the kind of people who, when something interesting is happening nearby, want to understand it. And as they listened, they noticed the Doppler shift, that slight change in frequency as the satellite moved toward them and then away. The same effect that makes a passing ambulance sound higher pitched as it approaches and lower pitched as it recedes. Guyer and Weifenbach realized that if you knew where you were on the ground, you could use the Doppler shift of the satellite signal to calculate the satellite's orbit precisely. You could work backwards from the changing frequency to the geometry of the path in the sky. And then someone, the story goes it was a colleague named Frank McClure, asked the inverse question. If you know the satellite's orbit precisely, could you use the Doppler shift to work out where you are on the ground? The answer was yes. This insight became the Transit Navigation System, the first operational satellite navigation system in the world, used by the U.S. Navy from the 1960s onward. And transit was the direct ancestor of GPS, the global positioning system that tells you where you are when you are driving to somewhere new, or walking in an unfamiliar city, or simply wondering on a still night exactly where on the surface of this enormous planet you happen to be standing. Two scientists listening to a beep out of curiosity, not assigned, not funded to do so, just listening. And from that listening eventually came the technology that means no one ever need be lost again. I think that is one of the most beautiful things about this whole story. The way that genuine curiosity, unhurried and unforced, kept producing things that nobody planned for. The ionospheric turbulence that Alpert discovered, the micrometeoroid density that was lower than expected, the navigation system that emerged from two people being interested in a radio signal. Sputnik asked questions by existing, and humans, being the wonderfully curious creatures that we are, could not help but answer them. Let that carry you now. The image of someone staying late in a laboratory, headphones on, listening to a beep from space and asking themselves quietly, what does this mean? What can I learn from this? What is this telling me? You are surrounded by the results of that kind of attention, by centuries of people who listened carefully and followed the thread wherever it led. You are lying in a warm bed, on a planet, in an orbit around a star, in a galaxy full of other stars. And somewhere out there, right now, there are satellites circling above you, doing their quiet work, descended, every one of them, from a polished sphere that beeped for 22 days in 1957. Sleep well. There is so much more universe to explore, but it will all still be there when you wake up. Before we continue on our journey tonight, I just wanted to take a very brief, gentle moment to mention something. If you are here because sleep does not come easily to you, first of all, you are not alone. So many people struggle with this, and we are really glad you found your way to this channel. In the description below this video, I try to keep an updated list of things that have genuinely helped people sleep better. It might be a book, a product, something worth reading, nothing pushy, just quiet recommendations offered with care, in case anything there might help you too. Have a little look when you wake up. If you are curious, no pressure at all. Drifting back to Earth And so, here we are, at the end of our journey together tonight. We have traveled quite a distance, you and I, from a drawing board in Moscow, where an ambitious scientific laboratory was quietly set aside in favor of something simpler and more beautiful, to a launch pad on the Kazakh steppe, surrounded by flat land and enormous sky, to the ionosphere itself, that turbulent, electric, endlessly surprising layer of our atmosphere that nobody had ever seen from above before. We followed a beep around the world. We listened with scientists in their laboratories, with amateur radio operators in their gardens, with Bernard Lovell at his enormous dish in the Cheshire countryside. We watched two curious researchers at Johns Hopkins follow a thread of Doppler-shifted sound all the way to what eventually became GPS. We watched a nation reorganize its schools, create new institutions, ask harder questions of itself. We watched international law quietly reshape itself around the fact of a small silver sphere passing overhead without asking permission. And through all of it, at the center of everything, that modest little object, 83.5 kilograms, 58 centimeters across, polished to a mirror finish, filled with nitrogen and silver zinc batteries and magnetically latching relays, 4 antennas trailing behind it like the tail of a comet, the simplest satellite. There is something I keep coming back to as we reach the end of this evening together. It is the name Prostashi Sputnik, the simplest satellite. Korolev and his team called it that almost apologetically, as though it were a lesser thing than what they had originally planned, a compromise, a workaround, something to do while the real work caught up. And yet, the simplest satellite revealed that the ionosphere had weather, that the upper atmosphere was 9 times denser than anyone had calculated, that micrometeoroids were rarer in low Earth orbit than the models predicted, that the Earth itself is not quite round, not quite symmetrical, slightly pear-shaped in a way that matters enormously when you are trying to calculate a precise orbit or aim a missile or land a spacecraft safely. The simplest satellite created NASA and DARPA and rewrote the education system of the most powerful country on Earth. It established the legal framework under which every satellite in orbit today operates. It inspired GPS. It proved that living creatures could survive launch and weightlessness. It started a conversation between nations about who owns space and arrived at the quiet and rather beautiful answer of nobody, and therefore everyone. Not bad for something that did nothing but beep. I think there is something worth holding on to in that as you drift toward sleep tonight. The idea that simplicity, done well, with care and precision and real understanding, can be more powerful than complexity. That the most important thing is often not the grandest thing. That a small, clear signal sent faithfully into the dark can travel further than anyone imagined. You have been wonderful company tonight. I hope your mind is a little quieter than it was when we began. I hope the images are soft and pleasant. A silver sphere in sunlight, the curve of the earth below, the stars above, unchanged and unhurried, exactly as they have always been. Now the music is going to carry you the rest of the way. Let it do whatever it wants to do. Let your mind go where it wants to go. You do not need to hold on to anything. You do not need to follow anything. Just let the sound be there, and let yourself be here, and let the rest take care of itself. The universe is very large and very old, and it has been getting along quite well for a considerable time. It can manage without your attention for a few hours, so let go, drift, sleep. We will be here again whenever you need us. Good night.